Hi everyone, I'm going to present my paper, Measure Anatomical Thickness from Cardiac MRI with Deep Neural Networks. There are 3 parts in my presentation. First, let's look at introduction. What's wall thickness? Wall thickness is determined by the Euclidean distance between the corresponding points on the inner and outer wall borders. Let's look at this example. It's the thickness of the myocardium. We should calculate the distance between the epicardium and endocardium. Wall thickness is very important for disease diagnosis. For example, abnormal changes of the left ventricular myocardium thickness are signs of many heart disease. There are 2 different kinds of cardiac wall thickness. The first one is rational wall thickness. We can separate the heart into 6 different parts and calculate the average thickness in these 6 parts. So in all, there are 6 values. For dense wall thickness, we should provide the thickness at every position in between 2 walls. Since dense wall thickness is more explainable and has more information, in this work, we will focus on dense wall thickness. Here, we provide the overview of dense thickness computation using the mathematical model. Given any shape, for example, an annular binary mask, we first solve the Laplace equation to obey the equal potential surface and adopt Euler method to integrate the tangent vectors. Finally, an interpolation algorithm is performed. More details, please refer to our paper. Since we need an iterative method to compute the Laplace equation and Euler's method, therefore the mathematical model is slow and it depends on the thickness and the step size in Euler's method. So this is the limitation of the current dense wall thickness method. It's pretty slow. So this gives us opportunities. Inspired by the current deep learning-based method for PDE solving, which can offer guarantee for converge and achieves 2 to 3 times speed up. Therefore, we want to use the mathematical model to generate the ground truth wall thickness and propose our deep learning-based method for cardiac dense thickness estimation. First, we've proposed a fast solver to estimate the thickness from a binary image. It will have a unit architecture. Our target is to minimize the difference between the predicted thickness and the ground truth thickness, which is calculated from the mathematical model. We propose a loss function as follows. We want to minimize the L2 difference between the predicted thickness and the ground truth thickness, and add another L1 regularization to force the sparsity on the predicted thickness. And we also propose an end-to-end network that it takes a raw image as input and predict both the segmentation and the thickness. It perceives the shape during thickness estimation by learning the segmentation of the heart. It enforces the decoder of the thickness estimator to utilize the features generated from the segmentation decoder via feature map concatenation. The reason why we decompose the thickness estimation into 2 subnetworks is that we found that it's non-trivial to directly predict the dense thickness from a raw image, since it needs to infer a shape as how it works from the mathematical method and our proposed fast solver. Therefore, we propose our novel end-to-end network that utilizes the semantic features from the segmentation task. And there is another challenge. when we train the model with combined segmentation and thickness loss, the segmentation will dominate the training, and the thickness estimation is not able to converge. Because the predicted shape as hat is inconsistent with the shape of the thickness ground truth Y, because Y is from the ground truth segmentation. We cannot guarantee the S and S hat is 100 the same. So we cannot use the ground truth thickness Y as the guidance for predicting the thickness. Our solution is use the S hat as input to our fast solver to generate a pseudo thickness, and want our predicted thickness Y hat to be consistent with our pseudo thickness. So this is the new loss function. We want the Y hat to be consistent with the new pseudo thickness. We perform our method on 2 different data sets. One is ACDC, which has 5 different categories and have a different distribution of the thickness in different category. But because it has limited amount of label data and the annotation is expensive, so we propose another data set that is a synthetic data set, which is generated from our synthetic data, which is inspired by the deep learning-based PDE that it proposed that the PDE solver can generalize to different boundary conditions. And this is the step to how we generate the synthetic data. This data has contains over 6,000 images, and the range of thickness is wider compared to the ACDC data. And because there's no other deep learning-based dense thickness estimation method, so we compare with the autoencoder. We found that our proposed fast solver with a UNet4, which is has 4-time downsampling and upsampling, performs the best. And this is the visualization result. We found that the model trained with the synthetic data perform better compared to other methods. And we also test our model on 3 other data sets to evaluate the model generalizabilities. We also found that the model trained with synthetic data performed the best. And this is the visualization result. And for the end-to-end model, we also compared to 2 different baselines. One is UNet, and the other one is the end-to-end model trained with the loss function with the ground truth thickness. And our model, our proposed method is trained by the pseudo thickness. We can see the model trained with pseudo thickness performed the best. And this is the visualization result. From these examples, we can see that the model trained with the pseudo thickness performed the best compared to other methods. Suppose look at the white arrows here. We also provide the thickness patterns using the 17 segment models. We can see different disease or pathologies have different thickness patterns, which shows our clinical value of our proposed method. And for more details, welcome to read the paper. And that's all. Thank you.